important announcement. So you have your exam. You are talking about your exam. So your exam is a quiz, basically scheduled on Monday after that. After the talk of Dr. Murala at 6:30. So it will be an objective type of quiz, maybe 40 minutes duration and 20 questions. So please make sure to attend those that quiz, because for getting, because many of you are concerned about your certificates and all. So this is mandatory to clear that quiz, right? So please attend. Durgesh, please drop a message also on this chat, right? So let me begin. So today I will take up, as I told you, I will take up this topic, deep learning and convolutional neural network. So now we, as you all know, we are running this program also. We say that, okay, regarding quiz, you want me to repeat? Okay, let me repeat it. Your quiz is scheduled on Monday after the talk of Dr. Murala at 6:30 p.m. It will be an objective quiz, maybe 20 questions of 40 minutes duration. So you will be shared a Google, the quiz will be in the form of Google form. You can you can take up it that. So we'll share it with you. Now let me do this. We can have, if there is any other question, we can take it at the end of the program. Let me begin with the today's talk first. So deep learning today, right? So we all know that artificial intelligence, deep learning, these are the buzzwords, and that is why you are also doing these courses. So how this happens? This happens why these things are so much, these words are so much popular, because artificial intelligence actually has penetrated, as it is written here, practically every aspect of human life, right? And what is the catalyst behind it? That is deep learning. So artificial intelligence is not a new word, right? For those who are working in this area, it was because we know that fifth generation computers, and then Japanese have given the concept, and then so many things have been done. But how this has become important today? What is the main catalyst behind it? That is deep learning. So now you can see that with this picture, that in fact artificial intelligence, or you can say that deep learning, is everywhere. So you can see here a lot many applications are being jotted on this slide. You can see that for image classification, speech recognition, language translation, language processing, recommender system, right? That is the most, the application you are aware of. So you just search on some e-commerce platform, or like Google, in any site, you just search and then it will show you the advertisement related with that, right? So recommender system. Then another important area is there, that is medicine and biology, right? Lot many systems are being developed now, which may be helpful, because we know that the experts, right, in the medical, they are in scarcity, right? Demand is more than supply, you can say. So here, if you have seen a few days ago, like a clip was shared, that is from Sundar Pichai ji, that they have also developed a device that they have given to a hospital at Hyderabad, and so that is taking care of this glaucoma. So so what is happening with that machine? Not only the screening, but the decision whether the eye is having any problem, or what is the grading of that disease, that can also be done, right? So in fact, in medical imaging, all the areas of medical field, the deep learning based classification systems and disease grading systems, they are becoming very popular. So Samir, who has conducted your session yesterday, and he will so he is also working on capsule endoscopy, right? So how to detect that cancer and all. So then we have media and entertainment, right? Nowadays, video captioning, real-time translation, and these days, if you have seen that earlier, we Now, based on the story, the videos are being created. So Microsoft has given, and then some other systems are there. If you're not aware, then please see to it. And then, of course, in security and defense, these surveillance systems, right, satellite imagery through, they are very important, because like you must have seen in movies also, that someone sitting in US knows that who is driving a car on which is street, right? So then these autonomous machines, like everyone wants to get that Tesla, right? So this autonomous cars, and so the detection required so many quick decisions, right? You can see that when the car is moving on the road, you need to not only identify traffic signals, but also many objects there. Now, objects may be of variety of types, like there may be a paper bag also on the road, and there may be a child on the road. So how to take decision based on that, right? So deep learning based systems are developed for every of these scenarios, and that is how we are finding it useful today. So what is deep learning now? So we understood, like, it is so and so, but what it is actually? So see that deep learning is nothing but a machine learning technique which allows computers to learn as well as improve the performance with the experience and data. So it's like a child. So when you were a kid, you have seen that flame for the first time, right? So your mother must have told you, okay, don't touch, you will get hurt. But then sometime we touch and then we know, right? So since childhood, we are looking at various things, and we are learning through that, and that is what we are doing here in the deep learning. So it actually provides you a great flexibility as well as power, so to learn the word as a nested hierarchy of concept, because we know that we actually learn that way only, right? So if you say, okay, we see small things, and based on those small things, we build up the concepts there, right? So we can say that each concept is defined in terms of simpler concepts. So in other words, we can say that it is a more abstract representations computed in terms of less abstract ones, right? So we'll see more to it. And then so if you see, we started, the course name was AI and ML, then we come to DL. So how they are connected with each other. So see here, AI is a bigger umbrella, right? Under which machine learning is there, and within machine learning, deep learning is there, right? So we can say that when, as I was telling you, the concept of the fifth generation computers came, then we want computers to mimic the human behavior, right? And at that time, these systems were based on basically knowledge representation and this systems were there. Now later on, what happens, that machine learning came to the picture, right? Where we developed those techniques where computers can learn without being explicitly programmed, right? So we are becoming more and more flexible. Then came deep learning. So deep learning is a subset of machine learning which makes this you just studied this neural network. So multi-layered neural network, right? Because multi-layered neural network, it requires a lot of computation, right? You have heard about. So you have already learned these things. So this is a subset of machine learning that makes computation of the multi-layered neural network feasible. Are you experiencing some other voice also from my end? Because some construction is going on actually in the nearby. Then I need to change the place. Okay. Okay, good. Because I mean, in nearby some construction is going on, so I am having that voice. Okay, good. Thank you. So AI, ML, and then DL, right? So if you see that the three paradigms of artificial intelligence systems. So first one, we say that rule-based systems. Rule-based systems, basically, if you say that right now we are talking about a system for disease diagnosis. So what was there? There were, if you say such system, then the earlier system, they were the rule-based. So you'll say that, okay, I have a headache, I have a running nose, so I have this symptom. It means that I have a flu, that type of thing. So those systems, the new rules are to be added. And then, so you can say that based on those rules, some hand designed programs were there with which the system worked. Then we have classic machine learning based systems where what we have input, then which you have already done, that we have this hand design features, and then so in the middle of the class you are writing when we are getting certificate. Are you attending this course for certificate only? Just wait for lecture to finish and then we are taking up your question. Of course, you can't get it right now. You will get it only after completion of the course. So let the lectures finish and then we will take up all these things, right? We are taking every day. Don't, I mean, so if you have any question related with the concept we are going on, please drop the message, because I need to take up that chat that is visible, right? So then we have machine learning based systems, so where we have hand design features. So if you look at the literature, then several sort of features have been designed based on the problems, based on the nature of the problems, basically. And then we came finally to the representation learning, where we have this deep learning, where the features, as I told you, the more abstract representations computed in terms of less abstract ones, right? So the features are basically my system, my model learns features from the example data, and then the features are being mapped, and the task, whatever task you want, that is to be done, right? So these are the three paradigms of AI. Now, if we go to, we'll say that how we are having many good algorithms, a lot much work has been done where we have used machine learning system. So what was the issue with the traditional machine learning system? So that, I mean, now we are doing a lot of work with deep learning, right? So if you look at this picture, which is just showing you the traditional machine learning system. So you have this picture. Now from this picture, the features are being extracted, and from the extracted features, the system is being trained. And once the system is trained, then then this new image comes. So that again the features are being extracted, and now the trained system is already there, and that system tells what about this picture, right? So what are the limitations there with the traditional machine learning system? That we are having manually designed features. So many like features based on color, texture, shape, right? Color histograms, like this heraldic textures. I mean, so many features are there. Zernike movements for shape, and so many. The literature is full, right, of features. So traditional, here you can see that we are in the traditional ML we use manually designed features, right? And more, I mean, manually, if we go for manually designed features, then more often they are over specified, right, as well as incomplete, right? If, as I told you, that basically when I am working on some problem, so I have designed that feature which is more suitable for my problem, right? It may not be suitable for some other problem, some other domain, some other applications, right? So most of these methods, they were mostly application dependent, and they were also time consuming in design and validation, because we need to see, like, you are designing something, then it is working, not working, like that. Then another issue was that, as I told you, that every one of us, like, we are working on the problems, and everyone is working on designing these handicraft features. So this development of this was a costly as well as complex job, right? It is not easy, right? There is nothing that you just see the problem and will understand, okay, I'm going to go choose this feature, and my job is done, right? A lot of work is required to do. And then there is another very important term here, which is try to understand, because you will find this word at many places: curse of dimensionality. Now, what is curse of dimensionality? Let us say we have n number of pictures, right? N number of input, right? And so we are extracting F1 features, right? So and then we are getting some performance, right? Let us say the accuracy that we are doing this classification, and the accuracy is 80%, right? Now, when we increase the number of features on the same data, then performance increases, right? So let us say from 80, it became 82, right? I'm again increasing it, F3, let us say it becomes 86. But if I'm going on increasing further, my performance will not increase that. So this is we call as curse of dimensionality. So now let us see with this drawbacks where deep learning comes into. So this is your machine learning, traditional machine learning framework. So here you can see this is your input, this is your feature extractor, which extract features there. And this is, as I told you, this is the manual task. And then there is classification, right? So here there is a classifier, machine learning classifier, which performs, which is actually automatically trained based on the features extracted from the training images. And then when at the test time, when some input comes, then it gives you output. For example, we are saying classification, so it is a cat. Now, what is there in deep learning, right? So in the deep learning, it is, basically we say that it is an end-to-end learning. So the training is automated. When we present a bulk of data, right, to my model or my machine, then my algorithm. So then what happens that it automatically learns from those data, from those, here we are saying images, okay, from those images. And then when we present at the test time, we present a picture, it classifies it, right? So that is the difference between the machine learning and deep learning. So what is there in deep learning? As I told you that more abstract representation into developed based on less abstract ones. So here, so here you can see that from the picture, right? So here the features are extracted at different levels, right? For example, see from this picture, we have extracted some low level features. Now, based on these low level features, mid level features, based on this mid level features, here you can see this. So here you can see high level features. And so basically you can see that we are having a hierarchy of features, right? Hierarchical representation of features, low level, mid level, high level, that is right. And this gives us a very flexible, learnable framework, right? And here what happens that trained algorithms work for a broad range of problem. I was present in the day before yesterday, I believe, in the session when you were asking about transfer learning, right? And the experts were explaining you. So the algorithms were there trained. If you don't have enough data in one area, you may use your network, which is trained on the similar data, and then you can fine tune the final layers, right? So here trained algorithms may work for broad range of problems. So how do we learn the hierarchy of feature extractors? So let me come at that point, right, Tamanna? Let me come to that point. So here, so as I told you that we are learning a hierarchy of feature extractions, right? So we are learning useful higher level features from the images. So you can see that from the picture. Okay, just a minute. Yeah. So the details are there in the next slide here. So here you can see that as I'm going to explain you how we are learning this hierarchical representation. So what is there on this slide, that is what is explained in the next slide in detail, right? So we are learning these from the picture, because what happens if you look at this picture, in this picture we have only pixel values. So if you are aware of this concept of picture, we know that in the picture there we have pixel data only. So you can see that every pixel here is having what data? Intensity value, right? It is a color image. So every pixel is having this R, G and B value. So every pixel made up of red color, green color and blue color, right? So we have only this data. And from this data, we need to find out whether this is a picture of a cat or a dog or a bird or a flower, like that, right? So how we are doing this, that is what we are learning. So let us see here. So how we are going to learn the useful higher level features from the images. So you can see that here my input data is there, right? So if I ask you to tell me what is there in the picture. So you will tell me, okay, there is a human sitting here. His face is, if I ask you to just find out what is there, so you'll say, okay, a face is there. Now in the face, eyes are there, nose is there, mouth is there, right? Like that. But how do a computer algorithm will come to know, basically, right? So because at the base level, if you say that with this picture, we have only this data, color data, you can say, okay, that this pixel is of this color, this pixel is of blue color, this pixel is of skin color, this pixel is of black color, this pixel is of brown color, like that. So we have, so basically picture is nothing but a 2D array, right? And in this 2D array, every element which we call as a pixel is having intensity value, and it is a color image, so intensity value in terms of R, G, and B values, red, green, and blue values, right? So we have that data. From that data, we can see and we can tell, okay, a human is there, eyes are there, mouth is there. So, but how a computer will come to know from those values, from those numbers, that what this picture is all about, right? So here you can see that if we have this picture, so in this picture we just have this pixel data, right? So which pixel is of which color, right? Now from those pixel information, right, we extract low level features, right? So you can say that from the picture we can see, okay, where are the edges? So first layer you can see here, made up of edges. Then we have, okay, now these edges are this edge information that is being manipulated, and that is how we obtain that, okay, these are the object parts, right? Once we identified object parts, that, okay, these are eyes, this is mouth, and then let us say in the higher layer we are finding out the object. So that is how we say that we in the input is your image pixel. From pixels we get edge information. Let us say by using that information we are getting texture information, shape information, and finally we are getting the object information, right? So we say that each layer is actually a hierarchy. Each layer here extracts features from the output of the previous layer. You can see that this layer is getting feature from this layer is getting feature from this layer, like that. Okay, so each layer of hierarchy is extracting features from the output of previous layer, and then these layers, actually we'll see that these layers have nearly same structure, right? And remember that they are not being trained separately, because you can see that output of previous layer works for as an input for this layer, right? So what happens? These layers are trained in a joint fashion. These layers are trained jointly. Okay. So we'll say that how it is how this works, how this is good, because here the features which are learned in this manner, they are easy to adapt as well as fast to learn, because we said that in the traditional machine learning that they are complex, they are the problem is specific, so here the learn feature are easy to adapt and fast to learn, and here these they can learn both unsupervised as well as supervised way, right? And this, we can say that deep learning is effective end-to-end joint system learning. Okay, here you can see end-to joint system, right? We are not training them separately, and also it utilize remember that it utilize, because everything is learned by itself based on the examples, so we need lot of examples to learn a pattern, basically. Okay, so basically someone, like if you want to know about someone, okay, how is his habits, and also you need to observe, right? How he talks, how he works, how so you are going to observe him lot of for a good amount of time, and then you can say, okay, yes, this is how he is behaving, right? So here we can say then in 2010 basically deep learning is started, right, outperforming the machine learning technology, right? So it has started first in the speech and vision, and then in the NLP, right? So now what are the deep learning ingredients? So first thing is your artificial neural network, because we know that now the network which is so we want that the machine should work like human brain. So like we are having neurons, similar way here, based on that, we are going to learn the concept with the examples. So here also we have artificial neural networks, which are based on the concept of perceptrons. And so like we are having neurons there as a basic building block here. The perceptrons are the basic building blocks. Then we need data is there, because from the data examples only we are learning. And then we have algorithms to uh, train our artificial neural network, right? And to do all this thing, we need a lot of computing resources, right? So we need, if to start working with, we need these things. Now, so what is the success mantra here? How this deep learning has become popular? As I told you that deep learning is actually not the new word. It was there in 90s also, but it has become more popular, right, since 2010, when our this computing facility has become available readily. Then this data input data was readily available. I mean, not readily, I must say, like more input data was available there. So remember that deep learning, basically, we are having, it is a, uh, I mean, having this, uh, first of all, we need algorithms, then we need computing power, we need big data, and then only thus, this is the success mantra, right? So now we have increased availability of data, significant improvement in the computing power, and so that is how we can increase our model size. So earlier, in the absence of that much computing power, GPUs, right? So it was not possible to go for a deeper model, right? But with significant improvement in the computing facility, you can go for increased model size, right? And here we have new way of learning representation. As I told you, the auto feature extraction automatically learns features, right? So deep neural network architectures can be generalized well, and they can address a broad range of applications. So there are several, like deep neural network architecture, convolutional neural, conventional neural network, which you have already done, then convolutional neural network, recurrent neural network. I mean, many concepts are coming every day, right? Here you can see VNet for segmentation. So based on the requirement, right? If you see, when you will start working, then you'll see that every day new models are coming. So today we will focus on convolutional neural network. That is our topic of discussion. So convolutional neural network, they are actually a class of deep neural network that most commonly applied actually to analyze the visual imagery, visual data, images, videos. So here you can see, as this is the one of the earliest CNN, which actually bring back this deep learning, right, into the front foot. So here you can see that this LeNet 5, right, that is the network, came in 1998, and it was there for this digits, right, letters identification there. Okay. So here you can see that input. Now, right now you are not able to understand this architecture, but we are going to study, and then you will be able to understand. But actually, as I told you, 2010 later on. So actually, it was AlexNet which came into 2012, and with which this deep learning era has taken a, I mean, there is no stop. It has taken us so much boom here. So what was the difference here? Here you can see that in the AlexNet we are having bigger model, right? Here we are having 7 layers. You can see this convolution 1, convolution 2, convolution 3, 4, 5, and then this fully connected layer, right? So 7 layers are there, and let me tell you how many units. 650,000 units were there, and we were using here, it was not possible to implement these with your CPU, so we are using GPUs for their implementation. And so let us see what happened so that this whole comes. Before coming to the CNN, I will tell you in brief. Just search this ImageNet word there, right? So what happens in 2006, I believe, and before that, Professor Feifei Li from Stanford University, she was working on the medical images, right? So at that time, people were working because the data was limited. So people were working more on the algorithms. They want their algorithms to work more efficiently. At that time, she decided, why only algorithm? She decided to work upon the quality of the input data. So she said, okay, we will work upon the data. So she took a lot emphasis, and then this visual data set came into the picture, which she launched in 2009. And this visual data set, ImageNet, that is having more than 15 million of labeled high resolution images, and which are covering 22,000 categories, right? And then this gave sufficient, data for researchers to work more upon. So then what happens, that this was a high quality data set, and very soon it became popular for image classification, object detection, object localization sort of problem, right? So the challenge was being posed every year, right? So some training data is being given, some task is being given, and then the winners are being find out. And how do they find out winner? They say that, okay, minimal top 1 and top 5 error rate. So let us say I'm saying this classification, or let us say I'm saying image search. So out of top 5, let us say top 5 error means that out of top 5 answers, how many errors are there? Or top 1 means that the first answer which it gives you, if it is an error or it is a good one, right? So that is how the winner is being assigned. And then it came, as I told you, this LXNet, right? So LXNet came in 2012, and this was the first CNN based winner. Before that, these models, right, in 10, 11, so machine learning based. But here this LXNet came, and after LXNet, like lot much is done in this direction. You can see that VGG, another network, then Google Net, and here you can see that ResNet. Right, ResNet 152 layers. So it started here. You can see this LXNet 8 layers, from 8 layers to 152 layers, right? So this much, performance is going to be improved. We are able to run this much heavy model on our machines. So that was the base point. So now with this, let us come to the neural network for the image data. So suppose our input is an image, right? So here our input is image, and so we need to classify that if this picture is containing a bird or not, right? So we are having a neural network here, you can see, and this neural network, we will pass on input image, and we want to see that whether it is a bird or not. So of course the network has to be trained first with a sufficient number of images, right? So here, let us say, so as I told you, in the images, what we have, so let us say this, with the pictures, we have size. So we say that 256 cross 256. What does it mean? It means that there are 256 scan lines, right? And 256 columns over there, right? So how many pixels are there in this picture? If this picture is a 256 cross 256 picture, 256 into 256, right? That is your how much? You can check 665 36, right? So these many pixels are there in this picture, right? And for every pixel we have the color information, right? So now let us say if we go for this neural network, right? Very simple. Input layer is there, then hidden layer, output layer, that is your decision layer. So here let us say, if what will be your, sorry, so what is the size of the input layer here? You can see how many neurons are there. And then let us say how many weight parameters. If I am saying that here in the hidden layer, just suppose that this hidden layer is having 1024 unit. Right now you can see 4 units are there. But let us say if my hidden layer contains 1024 units, just see how many weight parameters are supposed to be there. See, we have these many pixels. So what will be my input size? This is my input size. Here you can see 3, but when I will pass this picture, how many pixels are there? 66,536. So 66,536 will be the size of the input layer, right? And if I'm saying that my hidden layer contains 1024 units, then how many weight parameters will be there? For each pixel, see, for each pixel, there are 1024 weights, because 1024 units are there, right? So here you can see for this input, these 1, 2, 3, 4 weights are there, right? So here for each pixel, what is happening? 1024 weights will be there. So what is the total number of weights required? This 66,536 multiplied by 1024, right? It means that we need these many weight parameters, right? So but so you'll say that it is too much. How we are going to work with this now? So before moving further, let us analyze our data. So if we look at the image data, so these are the nothing but the pixel values. Okay, these are the pixel values. Let us say it is a grayscale image, right? So grayscale image, pixel values, pixels are having values in the range of 0 to 255, right? So white to black, there are several gray colors. So that is how 0 to 255. So these are, every pixel, as I told you, is having some value. So here these are the gray levels corresponding to that pixel. So this is your pixel values of a block of an image. Now, before moving further, let us analyze, let us see, can we find some pattern in this block? Just see if you can find some pattern in this block. See here, although this data is of high dimensionality, because see, even a small picture 256 cross 256, right? So many input. So the data is high dimensional, but what is to be observed here? This data is having redundancies. You can see that the pixel values are being repeated. If you look at this picture, right, this picture, so many pixels are, all these pixels are white. So you can see that repeated, right, redundant data. Some pixels here, they are blue. This pixel here, that is purple. This pixel here, that is green, like that, right? So this data, image data, is having redundancies, and then in the data you can find out some patterns over there. So you can see that this is a pattern, this is a pattern, and so wherever this pattern is repeated, right, we can see that what is the content? The content in the image, the same content will be there, right, if your pattern is repeated. Now let us see this. So when we go for a, let us say, so convolutional neural network. So if we go for here, let us say we see this shallow network. So we are having this, okay, a couple of hidden layers and then this output layer. So what is our, what is the main thing here? Because if we go for our network, then you can see that every input here, see, every input is connected with each of this hidden layer, right? So every input require these many weights. Now this again, here you can see this is connected with every input there, in every node there in the second hidden layer, right? So do we, because if we are saying this, but this is a dense network, right? So we need weights for all, because whenever a connection is there, we need this weight information. So we need so many weight information. So remember, the first question is being asked, right, by the, I mean, that do we need all these edges? Because this is a fully connected model, right? Each node is connected with every other node there, right? In the next layer, you can see. So do we really need this fully connected model? Or we can skip some of the weights, some of the connections can be skipped. Then also here you can see that each every input, it is having its a weight for each unit here. So is it possible, instead of having these unique weights, right, can we have some weights to be shared? Because if you look at the previous, I told you that here, how many weights are there? If your hidden layer contains 1024 unit, single layer, right? Here you can see single layer. But when you will go for network, multiple layers will be there. So even if it is a single layer, when we are saying, okay, 66536 inputs are there, that is being multiplied by 1024 units. So these many weights were there. So is it possible to share some of the weight? Means that some inputs are having same weight, right? Not a different one. So with these questions were being asked, and we got the answer in the form of convolutional neural network. And convolutional neural network are nothing but neural networks with 3D activations and weight sharing, right? So we'll say that we need to understand what is this 3D activation and weight sharing, right? Now, let us understand this. So to come on this, first of all, we need to understand some basics, right? So here, remember, if we go for image, the patterns which we are learning, they are very small as compared to the image size. For example, in this big image, if I want to identify eye, that is a small, right? That is a small, very small as compared to this image size, right? So if we say that is this, we can say that eye detector filter. Let us say we are having a filter. Its task is to detect eyes in the image. So when we are running this filter, right, when we are applying this filter on this image, then it gives me if any if the eye is present there. Okay, so we can say that instead of using that entire weight parameter matrix, right, if we can use a small pattern detector, then my job may be done. Because let us say I'm looking for this particular pattern, which is, let us say, for eye. So here, but the thing is that, let us say some pattern, right? Some small pattern, but this small pattern can appear anywhere in the picture. For example, if you look at this picture, you are having that eye detector, but this eye detector may be present at different positions in the image, right? So here you can see that once we have learned this eye detector, right, then we can apply this line detector, right? Sorry, eye detector, and then it will identify, it will tell me where eyes are located, right? So same detector can be move around, and it can detect eye at different position. No matter where eye is there, I am having eye detector, I'm applying it on the different places in the image, and I will find where eyes are present. Okay, so I hope this is clear up to this. So now let us go into the details, how this works. Okay, so convolutional neural network, what is the important point? That they use parameter sharing, which we talked about earlier. Can these parameters be shared, or parameters, can these weights may be shared or not? And then here we are making use of small pattern detectors, which we call as filters, right? And these filters are used to convolve over the entire image, right? So, okay, don't worry, I will tell you about what do you mean by convolve this filter over the entire image, right? And so, but the question comes that how do we get this filter? So these filters are actually learned through neural network training in the same way as we do in the fully connected network, right? So here in the convolutional neural network, what we learn filters, right? So we learn filter coefficients basically, right? And each filter basically for different pattern. Okay. So just like we are having hidden layer in the fully connected layer, in the convolutional neural network, we have convolutional layers, right? I just showed you the neural network on the previous slide, and you also doing it from past 2-3 days. So we have hidden layers now, but in convolutional neural network, we have convolutional layer, right? And to handle large size of image data, right? Because images are of large size. So to handle large size of image data, pooling layers are introduced. So we will learn, don't worry. I mean, I know it is not making sense right now, but let me introduce you what is convolution layer and what is pooling layer. So I will give you the details. I will give you example of the parameter sharing. Don't worry. Then you will get it more clearly. Just wait. Here on this slide, there are several words you don't know right now, right? So let me introduce you those things first. Okay, so first of all, let us learn what is convolution operation. So convolution with an image block. Let us gives you a real number. How? Just see, this is your image. Just imagine that this is your image 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. This is your 8x8 image. Okay. Right. This is a small 3x3 filter. Okay. Now this is a because in the convolutional layers, as I told you, we are having filters. So we are learning filter coefficients, right? So let us say this is a filter. Okay. Now, this filter, this picture is to be convolved with this filter. So what we do is that we are going to place this filter here. Just imagine that we are placing this filter over this here, right? And what we do is that, so what is happening? We are going to multiply the corresponding term. So 3 will be multiplied with -1, 0 with 0, 1 with 1, -2 with 2, 6 with 0, 2 with 2. So you can see that the corresponding numbers written here, they are multiplied with the corresponding numbers here. And then we are going to add them, sum up. So we will get a number. Right. And in the output picture, what will happen? This center pixel will have that value, which we have just calculated by sum of product. So this is, so what will happen here? You have just placed this filter over here. Okay. You just see here. Okay. So you just place this filter over here. Just imagine that you have just put a piece of paper on this thing. You have put this thing on the top of this. So 3 comes under -1, 0 comes under 0, 1 comes under 1, 2 comes under -2. Just let me give you this example. You will get it very clearly. Let me complete it first. So 2 comes under -2, like that. So what is happening? We are multiplying the corresponding terms and we are adding them all. These we'll get 9 numbers. So when you will multiply, you can see that these are 2 blocks, right? 1 block in the image and 1 is your filter. So this is having your 9 numbers. This is having your 9 numbers, right? And the corresponding numbers are multiplied. Okay. The corresponding numbers are multiplied. So we will get these and then, so we will get these 9 numbers. And then we are going to add them. That will give me just 1 number. And what we'll do is that in the output, we will write this number at the place of this center pixel. So you can see this, when I'm placing this mask 3 cross 3 mask here, this is my center pixel. So what is the output here? That is being placed at the center pixel, right? This is the convolution operation. And this operation will be done when we want that every pixel should act as a center pixel. Means that we will repeat this filter, we will scroll this filter all over this image so that every pixel, right, should take the place of the central pixel where this filter is being placed. And then corresponding to that central pixel, the value is written in the output. Okay, let us see it in more detail. So now what is happening when we are sliding this filter over this entire image, right? Then we will get this array of real numbers, or this is called your filtered image, right? Filtered image. Output of filtering, applying convolutional operation on this picture by this filter. Okay. Now what happens here? What is there in the convolutional layer? In the convolutional layer, I will tell you what happens for the pixel on the edges. So convolutional layer, let me go one by one. Otherwise, it will be, so everything is in the planned manner. So just give me some time. So a convolutional layer actually has a number of filters that perform the convolutional operation. For example, let us say this is your input picture. Now in the input picture, now we have a number of filters. So in one layer, we are having a number of filters. So let us say one is your eye detector, another is your nose detector, another is your mouth detector, like that, right? So several filters, right, who are doing their own task, and accordingly, we will get the output. So let us say my input image is, so input image, I am applying 4 filters. So what is my output? I will get 4 outputs, right? So my image, I'm applying filter number 1, I get output number 1. I'm applying filter number 2, I'm getting output number 2, like that. Now see this process in detail, convolutional layer, what happens in the example. So please follow it with me and then let me know if you don't understand. So as I told you that this is my image, right? And this is my filter. So I'm going to place this filter on this picture, right? So here you can see, so that I'm going to place this filter so that the entire filter, right, is within this image boundary. So the first position where I can place this filter over this picture, that is this, right? Now, as I told you, what we are going to do, the corresponding numbers, right? So we can say that 5 is multiplied with 1, 1 is multiplied with 0, 7 is multiplied with -1, then this 7 will be multiplied with 2, this 2 will be multiplied with 0, this 5 is multiplied with -2, and like that. So we get these 9 numbers. You can see 5 into 1, 1 into 0, 7 into -1, 7 into 2, 2 into 0, 5 into -2. Then last row, 5 into 1, 3 into 1. See this? Sorry, 3 into 0, 3 into 0. Then this 5 into -1, right? And just add all these numbers. So you get 2. So what will happen in the output image? Okay, so I mean, in this example, the value is not changing, but what will happen in general, it will change. So in place on this pixel position, so let us say corresponding to this, we are having this output image, right? And so this is at the same position. What we are writing the new value which we got from here as a result of the convolution operation. Is it clear? Now, let me first, if it is not clear to anyone how we perform this convolution operation, please let me know. Okay. Now see here, how do we do here? You can see this image is converted into this single column, right? So image is converted into single column. So let us say these these are my 9 values from the image. So 517, 725. You can see 517, 725, and 535. So we are, it is a 2D data, but we are converting into 1D, right? So we are having a single column vector. And my filter coefficients are nothing but weights, because I'm see, there also you're multiplying inputs with the weights. Here we are multiplying inputs with the filter coefficient. So here my filter coefficients are the weights. Okay, so here this is my weight vector. So I'm writing here, see this 1 0 -1. Please switch off your video. 2 0 -2. Please switch off your video. Narayan, please switch off your video. No, these filters are typically taken of small size, 3 cross 3, 5 cross 5, 7. We can't take this filters large size, right? So if you take pictures, pictures are much larger size, right? Filters are taken odd size and small size, 3 cross 3, 5 cross 5. We don't take filters like 256 cross 256, right? As I told you, filters here, filters are what? Basically, they are the pattern detector, right? So small pattern there in the picture. That is what we are detecting with the help of filters. So now we are going to just do this calculating their dot product, right? So if you calculate the dot, how this is calculated in the system, just take the dot product of the two and you will get the response of the filter on this position. Now what will happen? See, earlier my filter was placed like this. Now I will move my filter. So now I will move my filter by one position here, and my next position is this. So next my filter is placed on this position, right? So I'm so again do the same process. Here 1 is multiplied with 1, 7 is multiplied with 0, and then this filter is what we have to learn, right? Filters are the weights. See, in the beginning we don't know what is the eye detector. That is what we have to learn through example. So what is happening in the beginning, all these filters, they are actually being given some random values, right? And then by doing this process of learning the filter, so that is what is done in the convolutional neural network. What we learn is actually filter coefficients, right? So filters are to be learned. So, but first just understand this. So what is happening now? We have moved our filter by 1 pixel. Again, we will do the same process. The corresponding coefficients are being multiplied and we will get one number, that is this -17. So in place of 5, you can just draw the similar size matrix here. And in place of 5, what we are going to write? We are going to write -17. So in the input, the pixel which was having value 5, in the output, that pixel is having value -17, right? That is how simple numbers we are doing this convolution process. And what will happen? This process will be repeated. Now, again, we have sliding it. Again, we are going to calculate this. So in place of 7, now we got this number -6. Then again, we will make this slide like this. Now you can see that if I am going to further shift this filter, then part of my filter will go outside. So we can't do that, right? So till when our shifting will be there? Just a minute. So till when our shifting will be there? Our shifting will be there till this. Okay. Okay. We can't shift beyond that. Okay. Now what is happening? So we have completed this, right? Now our filter runs horizontally. Now we will move vertically because this filter will move on the entire image. So what will happen in the next, my filter will be moved one place downwards like this. Right. Again, we will calculate a number which replaces this 3. Again, my filter will move one place right. Right. Again, a new value will be calculated, which will be replacing this 5. And this process continues till we reach at the end of any picture. Right. So now this is the simple process I showed you for if my image is a, let us say, grayscale image. So every pixel is having a value from 0 to 8-bit image. So let us say my pixel is having value from 0 to 255. But my images are colored images, right? So how do we perform convolution operation on red RGB images? RGB, red, green, and blue. So we can say that here basically every pixel, RGB image means that every pixel is having 3 values: R value, G value, and B value. Okay. So what we do is that, let us say I am having this 8x8 image. Right. So 8x8 image means 64 pixels, right? And each pixel is having R value, G value, and B value. So if we just separate out red value of each pixel, blue value of each pixel, green value of each pixel. So what I will get? I will get 3 planes: red plane, green plane, and blue plane. What do you mean by red plane? Here the pixels or the red component, right? Red component of all pixel, right? That is given in the R image. A green component of each picture we consider, that is. So again, remember that my RGB, they will also vary from 0 to 255. So my red images, the strength of the red, right, in terms of here 0 to 255. So that is how I got 3 planes here. And now, so you can see like this. Okay. So now I got my planes like I showed you earlier. Okay. So what will happen? So I will, when I need to take filter, now I need, because I am having 3 planes here. So you're talking about one image, but that is a color image. So for that image, we are having 3 planes. Okay. So I need 3 filters. So I will create 3 copies of the same filter. Right. So I have a filter. I'm making 3 copies of that filter, and each one of the R, G, and B image will be convolved with one of the filter. Okay. So what happens here? You can see, make 3 copies of the filter and apply convolution operation on each channel. Right. Now again, what will happen? We will get 3 values. For each channel. Let us say if I am having here 3 channels. So this is my pixel. Let us say this is my pixel. Okay. So this is the same position pixel. Okay. I'm applying filter here. When this pixel is a center one, I got 1 value. When I'm applying, when this pixel is a center, this filter, then I get 1 value. So I will get these 3 values. Now, how we will get the final value? We are going to add these 3 values to get a single output, because ultimately, see, we have made it in planes, but when you are going to see to it, you will see it as single image, right? So from these 3 planes, again, we have to form a single image, right? So how we'll form that? We'll apply convolution on these 3 planes, and at each pixel position, right? Let us say I'm having this 8x8 image, right? So I'm having 64 pixels. So first pixel, I got 1 for first pixel in red plane, I got 1 value. For first pixel in green plane, I got 1 value. For first pixel in blue plane, I got 1 value. So what will be the value of first pixel in the output image? the sum of these three values, right? So, similarly, let us say I'm talking about fifth pixel. Okay, so fifth pixel value in the after applying filter in the red plane, in the green plane, in the blue plane, these three values are being added, and that will be the value of the fifth pixel in the output image, right? So these values here you can see that corresponding to an image are component, G component and B component, right? Now this is your filter. So we have made 3 copies of this filter, and this filter, this image red, you can say red plane convolved with this filter, green plane convolved with this filter, blue plane convolved with this filter, like that, right? So we can have here, my filter size is 3 cross 3. Right now, here there is a word written stride that I will talk in a couple of moments. But right now, you can understand that we are placing filter here. We are moving it. As I told you, we are moving in the horizontal direction. When we reach at the end, we will move to the vertical direction, and like that. Again, after moving vertical, again horizontal, vertical, horizontal, like that, and we will get this output. Okay. And then what will happen? Here you can see that for when we apply this filter on the red component, we are getting this output. On the green component, this output. On the blue component, this output. How do we get this? Finally, as I told you, the corresponding locations, I need to add it. So 2 plus 1 plus 0, that, what is there? Okay, 2 plus 1 plus 0, you will say that it must be 3. But here we have another term that is called bias. So 2 plus 1 plus 0 plus 1, that is here 4, right? So here we can say that how this process is similar to what you do in the neural network. You can see that weight multiplied by input, right? So here we are saying, okay, weights are nothing but the filter coefficients. Okay, so these filter coefficients, we are going to apply the filtering operation or convolution operation on the picture. We are getting the value, and here we have added one more thing, that is bias. Now comes what is bias. Remember that here bias is actually introduced so that you can shift your now I will come to the activation function also later. On this output, basically we will apply activation function, which I will come later. So what happens that when you with the help of this bias term, you can shift your activation function to the left or right regardless of the input, right? If you notice that these terms, right, you can see that weight multiply with input, right? This is your input, right? So what is happening here, this bias term actually is not affected by the any of the input here. It is added, right, to it is you can say that a bias associated to that input. Because what is happening, we know that the problems, the real life problems, they are non-linear in nature. But if you look at this convolution process, this is linear. What we are doing, we are multiplying and then we are adding, right? So this is a linear process, right? So the most real world problems, they cannot be represented by this. So that is how a bias is being added here. Now see, let us see these things in more detail. And here you can see this is my 32 cross 32 cross 3 image. Cross 3, what do you mean by cross 3? Basically 32 cross 32 image is there. One is red plane, one is green plane, one is blue plane, right? So 32 cross 32. Now I am having, so as I told you, because in the image we have 3 planes, so my filter will also have 3 copies. So my filter is also extended 5 cross 5 cross 3. Now when I will convolve this, so I'm going to place this filter over this image, it will give me one number, right? How we get this one number? As I showed you, we are going to multiply this and then adding this, right? So here this WTX plus B, right? So that is how you get one number. Now this is what? This is your output of applying filter here on this input, and that is nothing but one hidden neuron in the next layer. So now when we will move this filter over this picture, we will get more neurons in the next layer. So you can see here, when I am going to move this filter across this picture, I will get this one plane. So this is the output of one filter, right? So remember that because I'm saying that I am using an this is how I used a word there in the beginning, 3D activation. What do you mean by 3D activation? See, one set of function, one filter will give you one slice in the output, right? Remember that there we have used 3 filters, right? So one filter applied with this R, with G, with B, right? That is how it is going to give you one slice, right? So what is happening if we want to get if we want to get this 3D output of depth D, we are going to use D different filters. Okay. And then it is this RGB there, and then one filter you are applying, that is giving you one output. Okay. Then we are applying one more filter, I will get one more layer. I will apply one more filter, I will get one more layer here. So here you can see that this is your output depth. And so you will get one set of weights, one slice corresponding to one filter, right? And in practice, what happens that your convolutional networks have so many filters, right? 64 to 1024 filters in one layer. So now, but here what is happening? We are going to, what do you mean by weight sharing? You'll see that we don't have these weights are being shared among the inputs, right? So with weight sharing, this process is called convolution. Now let us see weight sharing. So someone has asked question weight sharing, just look at here. Now let us say this is my image. As I told you earlier that we are going to arrange it in 1D. So we have written these image coefficients here like 3, 4, 7, 8, 9, right? Now what is happening? When I am going to have, let us say, a 3x3 filter. This is my 3, just a minute, 3x3 filter. Okay. So let us say these 9 colors. So this is of this value is denoted by red color. This is by green. This is by blue, like that. Okay. So, okay, let me write here this red, green and blue. Okay, remaining like that. So what is happening when I am going to place my filter here? What will happen? 3 will be multiplied by this, 4 will be multiplied by this, 7 will be multiplied by this, like that. Okay, which I have represented with the color. So I hope this is clear. Now what happens that, so now I'm shifting my filter. So this is the 9 coefficient. So 3, 4, 7, 9, 10, 12. See, when I have put my filter here. So these 9 values are participating. So 3, 4, 7 is participating. This 9, 10, 11, 12 is participating. 11, 14, 15 is participating, right? And they are multiplied with the corresponding terms. And we got, and then after multiplication and addition, we got this one term that is corresponding to this entry 10 in the output image. Now, when I am moving my filter, so when I am moving my filter is placed like this. So earlier, what happens that this component of the filter, which I have showed with the red color here or green color here, that is having some value. Let us say it is having value 2. So earlier 3 was multiplied with 2. When I'm placing this filter like this, now 4 will be multiplied by 2. So this is what do we mean by parameter sharing, weight sharing. So you can see 2, this 3 and 4, you can see with the help of these colors. So when the green color, you can see this 4 is having green color, you can see here. And then this 7 is having. So what is happening here? This is how we are going to share the weights. So similarly, what will happen? Let me tell you that, okay, just a minute. So let me place this filter like this. Let me place this filter here. Now what will happen? Corresponding to 10, which color will be there? See, the maroon one. Corresponding to 12, which color will be there? The green one. See here. See this. Corresponding to 10, corresponding to 12, corresponding to 13, it will be blue color. So the same coefficients are, because filter is filter coefficients, they are being used. The filter is actually moved across the picture. So every pixel is not, except the boundary one, the pixel are exposed to this filter. Okay. And that is how the filter coefficient, that is how the pixels here are sharing the filter coefficient. So earlier when my filter was at this position, so whatever filter coefficient was multiplied with 3, when my filter is in this position, the same weight is used to multiply with 4. When I'm placing it here, the same weight is used to multiply with 10. This is what we called as weight sharing. You can see that if you are having this neural network, we are having these 16. So we're having 16 weight parameters. But here I am having only 9 weight parameters, right? So it means that these 9 weights parameters, they are actually being shared. Right? So convolutional layer, you can say that they are hidden layer in which various inputs, they share the same single parameter, right? So I hope this meaning of weight sharing is clear. Now, so here you can see, okay, let us skip this. So now what is happening with 2 filters? Our output contains 2 channels. So we called it feature maps. Okay, so remember that my image RGB, I'm applying one filter, I'm getting one output. Another filter, I'm applying it again in the same manner as I told you, apply filter on the R, G and B plane separately, add it, and that is how you will get output image corresponding to that filter. Okay, so here let us say if I'm using 2 filters, my output will be 2 channels, and these are called feature maps, right? These are the feature maps, and each one you have got for each filter, right? And remember that here each feature map applies its own bias. So here you can see this is your input image, red, blue, green channels, 6 cross 6 cross 3, and then here it is your filter 3 cross 3, right? Now you are applying this filter on this image, you are getting this 4 cross 4 output. Why you are getting this 4 cross 4 output? Because someone of you has asked this question. What happens that when we are making this filter, we are placing this filter, when this filter is completely inside my picture, then I am getting the first value, that is for 6. It means that I do not get the response for these pixels, these border pixels, right? So that is why the size, my original picture is of size 6 cross 6, but my output is of 4 cross 4. Why? Because my filter is of 3 cross 3, and that is why I missed the outer this layers, outer this border pixels, right? So, and so this is your there. So, and then we are going to, when we are do this multiply addition, and then every feature map will have its own bias, and that is how you got this 4 cross 4. Similarly, you are output, and similarly you are applying filter 2 with its coefficient, and then again you are getting a 4 cross 4 output, and you just put them together here. You can say that my output is 4 cross 4 into 2. Into 2 means that, see, 3D activation. 3D okay, this is 4 cross 4 and then 2 channels. Okay, if we are using 5 filters, then we will have 5 channels, right? So that is how D filters, D channels. Now, so till now the things are there, and we have not make use of activation functions, right? So activation here, as I told you, this process, linear process, and then we need to introduce some non-linearity into it, right? So that is being done with the help of activation function. So activation function is applied on all entries of this feature map, right? So what is happening? Let us say here you got this when you get that one value as an output of filter, on that you apply that activation function, right? So activation function, as you have been told, and then we will get, that is your activation map. So when filter output I am getting, that is my filter map, right? And on that filter output, if I am applying activation function to each and every entry over there, I will get activation map. Just see to it here. So now let us say, and this process is being repeated for every filter. So let us say we have used 2 filters here. So on each filter map, we will apply activation function, and that is how we'll get activation map, right? So here you can see that we are, this is a 32 cross 32 image, and we are using 5 cross 5 filters. So we are going to get 6 separate activation maps, right? So activation maps, as I told you, is applied on all the entries of each feature map to get the activation map. So here you can see that I showed you up till this, I showed you process. We got 2 channels here. Now on each entry, if you apply this ReLU activation function, which is nothing but it is mapping the value between this 0 to this input value. So if you apply ReLU function on each of these entries, what you get, this is your activation. Right. So first apply this activation map on the feature map, add bias, and that is how you will get the activation map. Right. So here, this is an example of activation map where this ReLU example we have used. This ReLU does nothing but it outputs the maximum of 0 or input. Right. So whichever is maximum. So basically, negative values are being converted, right? So here you can see that this is your feature map, and when you apply ReLU function, this is your activation map, right? So feature map, activation map. So activation map, as you can see, it is a non-linear operation. So now here you can see this. This is an example of this CNN. So what is happening here? You can see that there are multiple layers. So this convolutional layer, what it has? There are 6 filters of size 5 cross 5. Okay, so this is a 32 cross 32 cross 3 picture, and then we are having this 6 filters 5 cross 5 cross 3, and as an output what we get, see here, in the output how many channels will be there, because we are using 6 filters, so 6 channels are there, right? Now see how we are getting this 28 cross 28 from 32 cross 32. See here, when our filter was 3 cross 3, so what is happening, top row and the left column, they are being left out when I started from the beginning, but now my filter is 5 cross 5. So center pixel, what is happening, this before center pixel there are 2 rows up, and then 2 columns left. So the first pixel which will participate, that will be after 2 rows and after 2 columns. So that is why my original picture was 32 cross 32, but my new picture is 28 cross 28, right? Then I use 10 filters. So now my output channel, how many channels are there? 10 channels are there. Then I am going to again use 5 cross 5 filter, but this time remember that earlier my original image was 32 cross 32 cross 3. So my filter was 5 cross 5, and I have taken 3 copies of that filter because my output here input volume was 3. Now my input is, now here if you can see here, it is 28 cross 6. So how many copies of that filter I need? I need 6 copies, right? So 5 cross 5 cross 6 filters, and that is how I will get this this 10, and then the size will be further reduced. So for 5 basically it will be reduced by this. Here you can see that 2 at the two top rows, 2 bottom rows, right? Similarly, 2 left columns, 2 right columns. But here again, I am going to lose that same thing. So from 28 cross 28 to 24 cross 24. And this goes on. Now here you can see that another example, if we just unravel this 3D cube and I just show you each layer separately, then you can see that this is my, let us say, input picture, right? And each filter here will give me one activation map. So let us, you can see here, these are small, right, filters, right? So these are 32 filters, and each filter is of size 5 cross 5. In the beginning, I have input image here. So here, 5 cross 5 filter, I need to take the multiple copies here, 3 copies. Now you can see when I am going to get this this filter here, right? I am going to get this first channel here, first layer you can see of activation map. Now the corresponding to every filter here, I am going to get a layer here. See here, right? So corresponding to every filter, I am getting one layer in this output. So this is an example where activation maps are shown for one of my student was doing work on ocular disease challenge. So for this input image, when we applied convolutional layer, so these are the activation maps plotted for you, just to for your view. Now, what happens if you look at here that one filter is responsible for one depth slice, or you can say one activation map. If you observe that some filters are detecting quite similar sort of pattern. Now, when the some filters are detecting similar sort of pattern, it means that they are redundant, right? Whatever thing we can do with, let us say, if I need a pen to write and I'm keeping 4 pens there, so I'm using only one at a time, right? The three are redundant, right? So why to use them? We can. So that is the question. So now we come to the convolutional layer. So here you can see that the number of filters, because see here what is happening, the number of filters should not be too small so that we fail to capture the content of the picture. The number of filters should not be too much, right? Too large, that we are using redundant filters, right? Redundant patterns identification. So convolutional layer, you can see the number of filters in a single convolutional layer, they are chosen by the user. So you will do it in the lab in the next session. And typically we choose a good number of filters so that we can extract a maximum number of features, right? So now again here now I think you know the answer of this question. What are we learning here? So in the beginning, we start with some random numbers with the filters, and then finally at the after this training process, right, what after doing this process of convolution, now what we are learning, we are actually learning the filter coefficient. So at the end, let us say we are learning, okay, this is the filter for eye pattern, this is the filter for nose pattern, like that, right? So we have used several filters, so different these filters, we are learning the filter coefficients, which are the my weights. But these weights are now, they are being shared by the input pixels. So here you can see these demos over there. So you'll get some live demo. So here now, see what happens here, because okay, we are running out of time. Okay, let me see how to complete it. So now during, as we saw that during convolution, the weights are sliding to generate output. So when I'm placing this, see, you can see this is an 8x8 input, but my output is 6x6, right? So why, what happens that when I'm placing this filter is being placed like this, I'm getting output for this pixel, right? So you can, I will give you the link, you can see the demo yourself, right? We don't have that time, you can see it afterwards. First you learn. Okay. So here we are getting value for this. So basically what happens, 8x8 picture, and this is 6x6 output. It means that we simply got this left column, right column, this and this, because we cannot place filter over here, because if we are placing filter on any of the pixel here, my filter will go outside image. So these pixels, output for these pixels, I am not considering. Okay. So if I am placing my filter like this is the output I am going to get. So this is the basically 6x. This is the result I will get. Now when I am moving it here, I am getting another output. This is the output for this pixel. Okay. Now I am moving here. This is the output for this pixel. This is the output for this pixel. Now what happens? This is the output for, sorry. This is the output for this pixel. Now, if I will move it further, so you can see that this pixel could not participate, because when I will move filter, I will put filter center here, my one part of my filter will move outside. So that is why I could not get output corresponding to this. So that is how we do, one pixel cut from here, one pixel cut from here. So that is how you can see that in the width, 2 pixels we have lost. We got 6. Similar thing will happen when we will do vertical placing, right? So you can see that when I'm placing it like this, I got this one. And when I'm placing it like this, I got value for this one. So I got how many values here? 1, 2, 3, 4, 5, and 6. I did not get values for here. Okay. So that is how my output is 8x8 to 6x6. So now, so here what is happening? I am moving my filter by 1 pixel, right? But let us say I am saying that I am moving by, I move it by 2 pixels. So first position, let us say this, and next is this. So here earlier what was happening? I was moving 1 pixel, right? Now I have moved, see here, 2 pixels, right? So this is what we called as stride. Okay, so now you can see that when my stride was 1, my output was 6 cross 6. But when my stride is 2, my output is 3 cross 3, right? So what is happening here? Why? Because see, when I am using stride 2, then one position is this, another position is this, and another position is this. Now I cannot move my filter here, because if I will move my filter 2 positions, then it will go out. Okay, so remember, see here 1, 2, and 3. 3 cross 3, right? So if I'm increasing stride, my output is further decreasing. Right, so here you can see what happens. My size becomes almost like half of the size of the input, right? So what is to be done with the image dimension? So that was the question asked by someone. So you can see here, when we apply this filter on this 32 cross 32 image, this 5 cross 5 filter, my output is of 28 cross 28, right? So size is reducing. Okay? And here the stride is 1. So what happens? The output volume. So remember that the operation with the filters, that is producing the output volume, and the filter values are initially chosen randomly. And gradually the values of the filters are updated, and each filter learns to detect a small pattern. And so what is happening? Can you tell me, if I am having an 256 cross 256 cross 3 my picture, and we are having 8 filters, each of size 5 cross 5, what will be output volume? So let us see. Each 5 cross 5 filter will be converted into 5 cross 5 cross 3 filter volume, because here you can see the volume is 3, so 3 copies of that filter. Now we will convolve each block of 5 cross 5 cross 3 in the image to get just one output value. So what will be my output? Remember, output layer will be of, see, 5 cross 5 filter. So what is the reduction? Reduction will be of 4, right? 2 right, 2 left, 2 top, 2 bottom, right? So here you can see what will be my output size, 252 cross 252. And what will be my output volume? So because we are using this for one filter, then one output volume, but we are using here 8 filters, so 8 layers, 8 channels will get, right? So my each channel will be of size 252 cross 252, and for each filter we will get one such slice, and that is how I will get 8 slices, each of 252 cross 252. Is it clear? Okay. Now here we just saw that dimension, how to take care of output dimension here. See here, so I used to do it by simple calculation, but for that there is a formula also. So like you saw earlier that when my filter is of size 3 cross 3, my 8 is my image size filter is 3 and stride is 1, then what is the size I will get? See, 5 plus 1 6. But when the stride is 2, what I will get? See this, right? So that is how you can calculate it, by using this formula also. So you can see that when we move on like this, the size of the output volume, that is, you can see it is decreasing, right? 32 cross 32 to 28 cross 28 to 24 cross 24. And because I said that every layer is having so many filters, so it will continually reduce. So what to do that? So how do we take care of dimension? We take care of this by using, there are padding basically, right? There are various methods. Zero padding is one of the common method. So here by using, we apply the concept of padding. So what happens that, let us say my image is 8 cross 8 and my filter is 3 cross 3. Now I know my filter is 3 cross 3, so it will reduce the dimension by 1. Top row will be and left column, similarly bottom row and right column will be chopped. So what I will do, I will provide from my side, I will pad, I will create. So you can see here that this is my original picture, right? So this is my picture, and when I am going to use 3 cross 3 filter, so I have added these 2 rows and 2 columns. Now when I am going to place my 3 cross 3 filter here, then I am going to get value for each and every pixel in this image, right? So this is the common method. I hope it is clear. Not clear, then raise your hand. So by using zero padding, dimension reduction is controlled, and by this way, corner pixels are giving their contribution. If we will not do, then what happens that till now, what was happening? That the corner pixels were not contributing. Okay. So just give me 5 to 10 minutes to complete it. I'm sorry, I'm running out of time, but let me complete it. So I hope this how this dimension is controlled, that is clear. Now, when you go in the image processing literature, there are several ways of padding, but zero padding is the most common. Okay, so that is what we are doing here. Now see, now let us say my input image is of size 7 cross 7, and I'm having 3 cross 3 filter applied with the stride 1. So what I will do, I will pad my picture with 1 pixel border. And then what will be my output? Simple, 7 cross. I showed you in the previous slide. So every pixel will now participate in that. Okay. So convolutional layers, mostly they use stride as 1, right? So now what should be the size of zero padding? Remember, it depends upon the filter. So when my filter was 3 cross 3, I have appended one one row at the top, one row at the bottom, like that. But if my filters will be of size 5 cross 5, अब क्या करना होगा? We need to append 2 rows above, 2 rows below, two zeros in the left side, 2 zeros in the right side. Okay. So just see, basically, just imagine that if you are placing your center of the filter at the corner, how much your filter is outside. So when you are placing center of the filter at the corner here, and your filter is 3 cross 3, you know that 1 and 1 are outside. Okay. But when you are placing this 5 center of the 5 cross 5 filter here, then you know that 2 rows above and 2 here left. So there the zero padding will be, as I told you, 2 rows above, 2 rows below, 2 columns left, 2 columns up. You can get it with this formula also, but I prefer to do this by practice. Okay. Now, let us take this example. Suppose we have this input volume of size 64 cross 64 cross 3. I'm applying 10 filters and each of size 5 cross 5. So, because see, the filter is of size 5 cross 5. If I want to keep the same size output, then the padding must be 2, right? And let us say stride is 1. So, what will be the output volume? See, here you know that because I am keeping padding as 2, so it will take care of my output volume size. So output volume will remain 64 there, right? And then how many channels will be produced? These 10 channels, right? So 10, because 10 filters are there. Okay. So what will be this? So what will be the size of the output volume? 64 cross 64 and multiply by 10, because 10 filters we are using. Now, number of parameters in the layer. See, number of parameters in one layer. So what is happening? Say for one layer, my filter is of size 5 cross 5 and 3 copies of that. 3 such filters we will learn. So parameters in each layer, 5 cross 5 cross 3. And remember, there is one bias, right? So 5 cross 5 cross 3, that is your plus 176. And how many filters are there? 10 filters are there. So how many parameters will be there in total? You will say that 76 into 10. Okay. So 760. So you can understand that your picture is of 4 cross 64. Otherwise, you need to learn how many parameters over there, which we talked. If you go for neural network, 66536, right? Corresponding to each pixel, you are getting a weight. But here, how many parameters you are learning? You are learning 76, right? See, let me repeat it again. See here, my input volume is 64 cross 64 cross 3, right? So 64 cross 64 picture, I am putting it RGB, so 3. Now I am using 10 filters, each of size 5 cross 5. Now so if I want to keep the same size, the padding should be 2, and here my padding is 2. So because the padding is 2, my output volume, what will be the the size of the picture will remain 64 cross 64. Why? Because we have done padding by 2 and my stride is 1. So remember, this output volume will be this 64 cross 64, and then how many filters I have used? 10 filters. So what will be my output volume? See, each channel, for each filter there will be response of 64 cross 64, then there are 10 filters, so this will be my output volume. And how many parameters are there in one layer? What is happening here? See, my filter is 5 cross 5 cross 3, right? See, because we need to keep 3 such filters. So how many? 75, and plus we are having bias value, so 76. So, and how many total parameters? See, each layer I'm having 76. How many layers I have? 10 layers, right? 10 filters or 10 layers. So 76 multiplied by 10, that is, so total parameters are 760, right? See, that is what I tell you, how to calculate padding. You can use this formula, right? Otherwise, as I told you, simple thing, like let us say this is my picture. So I have placed, if it is my 3 cross 3 filter, so center of the filter is placed at the corner. Okay. So what is out? This is out. So I need to add this. So that is how if my filter is of size 3 cross 3, I need to add this this one row of 0 and one column of 0. Similarly, when I will place my 3 cross 3 filter here, again I need to, because now this row is there and this column is there. Similarly on the other. So if my filter size is, remember that what is happening when my, see here, when my filter size is of when my filter size is of 3 cross 3, I am placing my filter here, then what is happening? I cannot calculate response of this pixel. So I can calculate response of this pixel only when I have appended these zeros here. Now by appending one row here and one column here and one row here, I can calculate the response of this. So for 3 cross 3 filter, how much I need to add? See here, one this row, one this row, one this column, and this. So what is my padding here? Padding is 1, right? So you need to pad it by 1. But my 1 means that one row up, one row down, one column left, one column right. Now when my filter becomes 5 cross 5 and I want to consider the response of this pixel. Ab kya hai hamara? Now what is happening? If I am placing my filter here, then 2 rows of the filter are up and 2 columns of the filter are to the left. So I need padding 2. Okay, so this is the rough way of calculating. If you want, you can simply use this formula, but try to learn in this way. So here, as I explained you, when you are choosing this size as 3, then you need to do padding by 1. If you are choosing size as 5 cross 5, you need to pad it by 2. So because here we have padded it by 2, so the output, in the output volume, the size will remain intact, right? Same. And 10 filters, so multiply by 10. Okay, I hope this is clear. So you can calculate, these are the formulas. Also, you can use these formulas. Now, finally, after convolution, we have fully connected layer. Remember that if you have fully connected layer, then what happens that you are, again, let us say my picture size is 32 cross 32 and cross 3. Then we need to flatten it first. And so my input vector is, when I write it in the, these are formulas given which I explained you. You can use it later, right? See, we are what we are doing. These filters in different layers, the different filters are there, and those filter coefficients we are learning. So it is not like what we are fixing up. We are fixing up. Let us say we are using this 3 cross 3 filters. When we are using 10 such filters, when you are using 10 filters, so these filters are having different coefficients, right? We can't predict it. They will learn their coefficients there, right? So yes, I mean, so when I'm choosing a filter, that filter is applied on the input image. I already told you that input image, when we say it is RGB channel, right? Then I'm applying that filter on these channels. I'm adding it up, and that is how I'm getting one channel, right, as an output. I hope I answered your question. So if I'm going for fully connected layer, so if I'm going to convert it into 1D, this is how 3072 into 1. And then if I'm having 10 units, 10 neurons in the first hidden layer, then each unit will look on the full input vectors. So how many parameters you need? See these 3072, every input vector is having its own own weight. So 3072 weights, and there are 10 such units we are using, right? And 10 by. So total trainable parameters will be this. While if I am using convolutional layer, let us say of size 3 cross 3 in the first convolutional layer of the network, then my training parameters will be only 280, right? So you can see that if in place of fully, how this is calculated 280, as I told you in the previous slide. Okay, so so you can see that moving from fully connected layer to convolutional layer, I mean, we can save so much, right? So only these here trainable parameters are huge as compared to this, right? So less number of parameters we are supposed to train. So here convolutional versus fully connected, like, so here you can see that these, when I'm taking this filter, the filters are these coefficients, they are being used for, I mean, several pixels here. They have the same multiplied with the same filter coefficients, right? So, okay, I think time is up. So just a minute. So this is weight sharing only. So let me skip this. Okay. So this is your CNN architecture. Here you can see that several convolutional layers are there. Convolutional layer, pooling layer, like that. And finally, we are having last layer as a fully connected feed-forward network, which does the classification, right? So these layers are repeated many times. We are training this network. We are learning filter coefficient, and once my network is learned, then it predicts, right, for the test image, right? So here, let me quickly tell you about the pooling layers. So here we know that what happens, this size of the these pooling layers are actually used for making representation smaller, right? So that our output volumes can be more manageable. Okay, so here you can see that if this is my image, because what happens, I'm using 64 filters, so now my output is having 64 channels, so the size is increasing. So how can we control to that? So here you can see that if we apply this pooling, means downsampling. So every alternate, let us say very simple way, every alternate pixels, if we are dropping, the size will become half of it, right? So from 224 cross 224, we get to 112 cross 112. Now, there are several ways of doing pooling: max pooling, average pooling, and min pooling. Just see max pooling. So see, this picture is of this 4 cross 4. Now I'm using 2 cross 2 filters, and with stride 2. So first filter placed here, second here, and I will take in each one, I will take the maximum of it. So out of these 4 values, the maximum one I will take. Out of these 4, the maximum one, right? So that is how, instead of this, the size will be further reduced. So that is how this example shows that corresponding to each box, we got one value, the maximum value in this box, right? That is your max pooling. Okay, so here you can see that from this 6 cross 6 image, we got 3 cross 3 image. Okay, similarly, there is average pooling. So here what will happen, again the same window, we are taking 2 cross 2 filter. So 4 pixel window is there, is right 2, we are going to take average of it, right? So these 4 values. Similarly, minimum, I will take minimum of it. Right, so this is min, max, and so pooling, remember, it is just a subsampling, and this doing this subsampling, we are not losing information of the this image, right? So that is how you can see. So now the last layer, that is the fully connected network. And here, you, as I told you, this is every time you are doing, you are getting a new representation here. And finally, this fully connected feed forward network through which you will do the classification. Okay. So this is your, just a minute. Okay. So I understand that, just a minute. So here, this is how, this is just an example of a convolutional neural network. Here you can see several layers are being interspersed, right? So, okay, so this was all about, just a minute. So I'm sorry I took more time. So somehow, so you can, any question or you can ask question. Yeah, I will share slides, no problem. Any question? If there is any question, you may ask. Otherwise, you may take rest. I'm sorry, I'm a bit, it took some time because initial slides would take some time. So I was about the end only, yeah.